Hello everyone. Welcome to this fourth lecture on the course of solar photovoltaic system design. And today's lecture we will be delving deeper into the solar radiation components. So if you remember in the last lecture we discussed about how the atmosphere interacts with the solar radiation and how the solar radiation intensity goes down as the radiation passes through the atmosphere, and how due to the scattering in the atmosphere there is a production of the diffused radiation. Then we also looked at the concept of air mass, which basically signifies the path length of radiation through the atmosphere. So in the last class we ended up at this particular graph which talked about the radiation at different points in the space as well as on the earth's surface. So the radiation AM0 here, the spectrum AM0, this, as we discussed last time, this is the spectrum just outside the earth's atmosphere. Whereas the AM 1.5 spectrum is considered the reference spectrum for solar PV. So why this particular spectrum has been chosen as the reference spectrum? There is a particular reason for that. So if you do a little bit of back calculation, in the last class we looked at that air mass is nothing but 1 by cos theta z, where cos theta z is the cosine of the zenith angle and theta z represents this particular zenith angle. So if we have radiation coming at a particular angle from the vertical, this angle is theta z. So if you do a little bit of back calculation, if you consider AM value equal to 1.5 and you do a little bit of back calculation to find out the theta z, the zenith angle corresponding to this particular value of air mass, you will get that this is somewhere around 48 degree of theta z corresponding to AM 1.5. Now the question might arise in your mind that why this is particular zenith angle is being considered, or why this particular air mass 1.5 is being considered as the reference spectrum. So the idea is that, as we understand, if you look at the variation of this zenith angle, so for a particular location, for a particular observer, let us say this is direction east and this is west. So as the sun rises in the east, the zenith angle would be around 90 degree, and then gradually as the sun goes up in the sky, the zenith angle reduces gradually from 90 degree, it comes down to 0 degrees, and then again after mid noon, as the sun proceeds towards the horizon on the western side towards the sunset, again theta z increases and goes to 90. So it starts from 90 in the morning, gradually reduces down to some lesser value, then goes to 0, and then again increases in the second half of the day, and then finally as the sun sets it is again 90 degree. So that minus 90 to 0 to 90, that is like the daily variation of the zenith angle or the theta z. So if I were to take a reference spectrum, the most common sense choice would be take zenith angle somewhere in between the 0 to 90 degree range. So if we were to take precisely as 45 degree, suppose if I take theta z as 45 degree, then that would correspond to air mass value of 1.414 and few more decimal places, which is also okay, which is very close by to the actual value taken as 1.5, but then this does not seem really that elegant, whereas AM 1.5 seems quite simple and elegant, and the zenith angle to which this AM 1.5 corresponds, that is also very close by to the mid value of 45 degree. So just for simplicity and ease of calculation, we have globally we have accepted AM 1.5 as the reference spectrum for solar PV. So with respect to that, we understand that AM 1.5 is the reference spectrum. So another question arises that why do we need a reference spectrum at all? So if we, let us say if we want to compare the operation of different solar cells, so if we want to have comparison between solar cells measured at different times and locations, then we need to have some standard. So, that is why we have defined some standard test conditions. And these standard test conditions are 3 in number. One is that the radiation intensity should be 1000 watt per meter square. Another is that the solar cell temperature should be equal to 25 degrees Celsius. And third is that the spectrum should be AM 1.5. So, AM 1.5 gives us the reference spectral breakup, which would constitute the standard or the reference spectrum. So, if any solar cell is operating under these conditions, then the output which we get, that we define as the rated output. Now, between these two, between 1000 watt per meter square and AM 1.5, again there is one linkage. To understand that linkage, we need to look at the spectrum once again and little bit in more detail. So, just in the previous slide we talked about AM 1.5, but then there are further classifications of this AM 1.5 as well. So, suppose if someone takes all the radiation into account, the direct radiation and the diffused radiation, everything into account, then they would get the spectrum known as AM 1.5G or global. Another option is that if someone does not take the diffused radiation into account, if they just take the direct radiation into account, then they would get AM 1.5D. So, there are these two options of spectrums, AM 1.5G and AM 1.5D, whereas G stands for the global radiation or the overall radiation and D stands for the direct radiation. Now, to understand the relationship between these two, AM 1.5G and AM 1.5D, we need to revisit this particular accounting of solar radiation intensity in the atmosphere. And if you remember, we discussed this in the last class, that out of the total incident radiation at the edge of the atmosphere, the total radiation which enters the atmosphere from outer space, 18% is absorbed, and around another 7% is scattered to earth and around 3% is scattered out to the external space. This is all accounting under the typical clear sky conditions. So, roughly speaking, we are getting almost around 70% of direct to earth radiation. So, if we do exact calculation, we can see that out of the total radiation which was incident outside the earth's atmosphere, so just outside the earth's atmosphere, this we call as AM0, right, or path length 0. When the radiation has not entered the atmosphere, it is just outside the earth's atmosphere, the path length through the atmosphere is 0, we call that as AM0. So, if I were to calculate the AM 1.5D with respect to AM0, so AM0 is there, AM 1.5D is this one, the direct to earth component. So, as you can see, from AM0 there is a 28% reduction to come down to AM 1.5D, right, 18% absorbed and 10% scattered. So, if I reduce the intensity of AM0 by around 28% overall, then I come down to AM 1.5D. And from AM 1.5D, if I want to go to AM 1.5G, which is basically the global radiation. So, as you can see, global radiation consists of two components. One is the direct to earth radiation, which is coming as a beam radiation or a direct radiation to the earth's surface, and another is the scattered radiation, which is coming as a diffused radiation. And also you can see, as you can look at the numbers in this slide, that under typical clear sky conditions, the ratio of direct to diffused is almost 10:1. So, that means that if I augment the AM 1.5D with another 10% radiation, then I end up with the AM 1.5G radiation. And this AM 1.5G is what is colloquially or simply called as AM 1.5. And this AM 1.5, if you were to do the integration of all the spectral intensities, so as we looked at the spectral graph across the entire wavelength range there were different spectral intensities. So, if you were to do the integration of all the spectral intensities across the entire wavelength range for the AM 1.5 spectrum, you will get that this value is somewhere around 970 watt per meter square, which again has been sort of rounded off to broad value of 1000 watt per meter square. So, that is how we arrive at that value of standard test conditions, that 1000 watt per meter square and AM 1.5, these two are tightly linked with each other. When you consider the AM 1.5 radiation, which is also called as the AM 1.5 G radiation, then the corresponding spectral intensity, the corresponding total radiation intensity would be 1000 watt per meter square. And to put everything into perspective on this discussion on spectrum and the associated radiation, we would get a graph like this. So, if I were to compare all three of them on the same set of axes, this is how they would compare. The red graph is AM 0, whereas if I reduce it by 28%, I come down to AM 1.5 D, or the green graph in this particular case, AM 1.5 direct. And then if I were to augment the AM 1.5 D with the diffused radiation, we will land on the blue graph, which is AM 1.5 G or AM 1.5 global. And also worth noting in this graph here is that if you look at the comparison between blue and green, the major difference is just in the visible region. So, that is where the diffused radiation is being produced. So, the major scattering or diffused radiation is mainly in the visible region, and if for the other regions, if you see, they are almost very closely overlapping, blue and green graphs. So, this is the standardized solar spectrum, the AM 1.5 G, or simply called as AM 1.5. This is the standardized solar spectrum, which is used as a standard for comparing the output of different solar cells, and this roughly corresponds to a intensity of around 1000 watt per meter square, which is also the another STC condition for comparing the output of different solar cells. So, now if we look at the phenomena through which diffused light is being produced in the atmosphere, then there are two major things which come into picture. It is basically the scattering of light, which produces the diffused radiation. So, the diffused radiation is nothing but a direct outcome of scattering of light in the atmosphere, and there are two major processes through which this scattering happens in the atmosphere. One is known as Rayleigh scattering, and Rayleigh scattering is the major phenomena which causes the scattering in the Earth's atmosphere, and this Rayleigh scattering is caused due to the molecules in the atmosphere, the gaseous molecules. So, the gaseous molecules in the atmosphere, they cause this Rayleigh scattering. And interesting thing is that this Rayleigh scattering is proportional to lambda to the power minus 4. So, the intensity or the amount of scattering which would happen due to Rayleigh scattering is inversely proportional to the fourth order of the wavelength of the light. So, what that means is that smaller the wavelength, the larger is the Rayleigh scattering. And then there is another phenomena also of scattering in the atmosphere, which is known as the Mie scattering, and this is mainly due to the aerosol particles and dust particles which are there in the atmosphere. Now, as you can probably appreciate that these aerosol particles and dust particles, they are sort of a varying phenomena. So, this is sort of a a varying or fluctuating thing from time to time, at different times of the day, in the different seasons of the year, the extent of aerosol particles or dust particles in the atmosphere would vary. So, this is a varying or fluctuating thing, whereas Rayleigh scattering is more of a permanent nature. It's always there because the composition of the atmospheric gases, they are more or less steady or constant at a particular location. So Rayleigh scattering is the base phenomena which is creating the diffused light through the scattering, whereas there is on top of that base phenomena there is superimposition of the varying or fluctuating Mie scattering. And now as you can see that we are saying that Rayleigh scattering is proportional to lambda to the power minus 4. So what it means is that smaller the wavelength, the higher is the amount of Rayleigh scattering, and that is precisely the reason why the sky appears to be blue. So if someone were to ask you that what is the reason why, if you look at the sky it looks blue, so the reason is that because if you look at the entire visible spectrum, so the violet, indigo, blue, that particular segment of the visible spectrum, the blue side of the spectrum is having a much lesser wavelength. Having a lesser wavelength, the scattering is much more, and because that particular component of spectrum is getting scattered to a very high degree, that is what our eyes perceive as the color of the sky. And it is only because of scattering that we see a color of the sky. If you go in the outer space, then the sky appears completely black because it is completely vacuum, there is no scattering. It is only the direct radiation which you can experience. So if there is a radiation coming from the sun disk to your retina, that is what you see, you are able to see that sun is there. But in all the other directions in the outer space, there is no scattering happening, so your eyes are not able to perceive any color, it is just completely black out there. But in the Earth's atmosphere, due to the scattering, there is a color which we see to the sky, and that particular color, as we just now discussed, is mainly due to the Rayleigh scattering. Rayleigh scattering has very high intensity for the lower wavelengths, and that is why the sky is appearing blue. So that is the phenomena which is creating this particular effect. So red light has a wavelength larger than most particles and remains unaffected, whereas blue light has a wavelength similar to the size of the particles in the atmosphere, and due to the phenomena of Rayleigh scattering, it is scattered to a much higher degree, and that is why the sky appears blue in general. So this scattering of radiation, it produces the diffused radiation, and this diffused radiation can sometimes be, the effect of clouds can be very, very intense. So this graph here on this particular slide very clearly demonstrates the extent of reduction in the solar radiation which can be there due to the clouds or due to the effect of scattering. So if you see here, this is the output current from a particular reference array, a PV array at a tilt angle of 60 degree in some location in Melbourne. And if you look at the two graphs, so there is one clear winter day output where you can see the radiation was very good, and therefore under typical clear sky conditions there was a huge amount of DNI, and the output current went up in the morning, peaked around afternoon and then came down in the evening, and there was a very high value. Whereas if you look at an overcast winter day at the same location, there is a very gradual little output in after a few hours of the sunrise, and then it is sort of remaining at a very low value, then peaking to a very small value and then coming down. And if you look at the comparison between the clear winter day and the overcast winter day, you see the output on the overcast winter day is hardly around 10% of that of the clear winter day. So that type of extreme effects can come due to the cloud conditions or the overcast conditions. So this is, and this on this particular overcast day, when we are having a completely overcast condition, complete cloud cover, then this entire output, whatever we see in the gray color, that is mainly due to the diffused radiation. So diffused radiation is there, but by definition diffused radiation will have a very low intensity as compared to the direct or the beam component of radiation. So this particular graph illustrates the extent of comparative level of direct and diffused radiation, and there can be a huge difference between the level of the two. So this particular figure here, it demonstrates the same different components of radiation which we have been talking about in little more detail. And as you can see, there is a direct component coming directly to the solar PV panel. Then there is some radiation which is getting absorbed and lost in the atmosphere. There is something which is getting scattered to the outer atmosphere, reflected. And then there is a diffused radiation which is produced due to the scattering towards the earth. And also the panel will have something which is known as the ground reflected radiation, reflected from the ground. So all those different components of radiation, they exist and can impact the output of a PV panel. So, there are these three components: direct, diffused and reflected. So, at this point it is important that we formally define these three components of radiation in a proper manner. So, there are these three components. The direct component is measured as DNI, also known as the direct normal irradiation. And this is like the beam component coming directly to the surface of the earth. So, if for an observer this direct normal irradiation is coming as a beam directly to that observer, and by definition as it says here normal, so it is measured perpendicular to the direction of the radiation. So, if this is the beam component of radiation, we measure it on a surface which is perpendicular to the direction of the radiation, and that is why the name direct normal irradiation. Then we have DHI, which is the diffused horizontal irradiation. So, we measure it on a horizontal surface. So, we have a horizontal surface and there is diffused radiation coming from all directions. So, we just measure it on a horizontal surface. And then GHI is the global horizontal irradiation, which again, as the name indicates, we are measuring it on a horizontal surface, and this is the net effect of DNI as well as DHI. So, together that effect is what we are calling as the global horizontal irradiation. However, please note that we cannot directly add DNI and DHI to get the GHI. So, if I were to say GHI equal to DNI plus DHI, then this is a wrong statement. We cannot directly add them. And why is that so? Because as we just now saw, by definition they are intrinsically different. Diffused radiation we are measuring on a horizontal surface. Global radiation again we are measuring on a horizontal surface. On the other hand, the DNI I am measuring on a surface which is perpendicular to the direction of the beam component of radiation. So, they are not defined on the same reference plane, that is why we cannot directly add them, but we can very simply derive that relationship between DNI, DHI and GHI. So, to derive that, let us try to understand it in little more detail. So, if let us say if I want to quantify the GHI using the DNI and DHI, and let us take a generic situation where let us say this is the vertical and the solar radiation is coming at some particular angle. We call this as the theta z, zenith angle, as we just now saw for air mass. So, the beam component is coming at some angle of theta z. So, this is my DNI component, and DHI as we just now discussed, it is just the total diffused radiation on the horizontal surface. Now, I am interested in finding at this instant when my DNI or the beam component is coming at a theta z angle to the vertical, I am interested in finding out what is the total global radiation or the GHI, global horizontal irradiation at this instant. Now, for sure, if I were to write this, I can write GHI is equal to DHI is exactly everything can be accounted for in GHI because both are being measured on the horizontal surface. But for DNI, I would like to take the component which is the effective normal radiation for the horizontal surface. So, because now GHI I am measuring on the horizontal surface, I need to take the projection of DNI which is in a direction perpendicular to the horizontal surface. So, if I take the projection of DNI on this vertical, that is what is the effective normal irradiation for the horizontal surface. And with simple trigonometry we can say that this particular component will be nothing but DNI into cos of theta z. So, if I take the projection of DNI on the vertical, I multiply DNI with the cosine of the solar zenith angle, then I get the direct normal irradiation with respect to the horizontal surface. So, therefore, this is the relationship which exists between these three. Global horizontal irradiation is equal to DHI directly plus the cos theta z multiplied by DNI. And therefore, it becomes very simple now that if I out of these three components, I do not need to measure all the three components. If I can measure two components, any two components, the third one I can find out. So, out of these three components, we only need to measure any two components. The third one we can simply tell if we can estimate the solar zenith angle. In a later class, we will look at the calculation or the formula for solar zenith angle, and we will see this is just a geometric parameter for the planet Earth, and for a given location on a given time of the day at a given day of the year, we can precisely calculate the solar zenith angle. And once we have the solar zenith angle, if we have any two components out of these three, then the third one can be easily found out. So, this is it for today's lecture, and in the next lecture we will look at little more details of how to measure these three components of radiation, DNI, DHI and GHI, and then we will further look at their applications. Thank you.